Hi, everyone. I'm Chris Sommers from Keysight Technologies, and today we're going to hear from Bert Klaps and Miroslaw Walukiewicz about speeding up network FPGA design using P4. Bert is a senior systems engineer, and Miroslaw is a principal engineer at Intel Corporation. I'm really interested to hear this talk because FPGA design is a really specialized and difficult skill. So anything that makes it easier to implement a custom data plane is a welcome addition to the developer's toolkit. Take it away, gentlemen.
Okay, thank you, Chris. And thank you all for attending this talk. So Miroslaw and myself work for Intel PSG. That's the Programmable Solutions Group, the part of Intel that deals with FPGAs. And as Chris already mentioned, programming FPGA using the traditional tool set like that's VHDL or Verilog language. That's a complex and time-consuming task, which requires highly skilled RTL developers. So P4 as a domain-specific language promises to make programming networking pipeline into FPGA significantly faster, and also integrating that with the control plane significantly faster. Over the past year, we have been using our pre-production Intel P4 compiler for FPGA targets on internal designs. And in this talk, we'd like to share our experience with one of those, a virtual cell site router reference design that was created by a team of engineers that did not have any RTL knowledge at all. So we designed a VCSR as part of the mobile, the MPLS mobile infrastructure, and integrated that with a commercial control plane. So with that, I'm going to give over to my colleague Miroslaw.
Okay, thank you very much for joining and attending this session. From this perspective, I want to talk about the mobile infrastructure, as I think it would be the most boring part of the presentation. Where the mobile infrastructure is present, because maybe you are aware of the data center, but the mobile infrastructure is the infrastructure or the devices inside of in the field where your mobile phone really talking. Yes, your mobile phone is talking to the radio unit over the front haul to the device, which is called the base station, and the base station is connected to the UPF and next components here after the UPF. We're presenting here the special use case of the base station, which was introduced by the 5G new radio or by ORAN specification, where the base station is divided between the two parts. Yes, one part is called the DU and the second part is called the CU. The DU means the distributed unit, the CU means the centralized unit. And today, this DU part is connected very close to the radio, to the antenna, as the radio is representing the antenna. And it is designed normally. It could be the separate box, or today many companies is making this device as the virtualized application, as the application running on the host, for example, in the Kubernetes, and connecting with some accelerators to make sure this application is the virtualized one. And the second box, normally the next box inside of the tower, antenna tower, in the antenna cabinet is the cell site router, which implements the mid-haul connection or the backhaul connection, which could be as Bert said, could be used the MPLS or in the future maybe the segment routing MPLS, and maybe in the more when we are talking about in the far future that maybe it will be segment routing V6. Why we are doing the FPGA, this model using the FPGA. First of all, for the FPGA use case, before we are talking about the P4, because today we have the two boxes, yes, and the space in the cabinet, the antenna cabinet, is very limited. There are people asking us, what happens if we can put this everything to the single box, to the single server, yes, running virtualized DU. We say, no problem, we have the FPGA, let's implement all the components inside of the FPGA. And to choose to speed up the development of this one, we just choose the P4. Of course, the P4 could be, you can imagine the other P4 implementation, like for example, UPF, like the central unit, all the NAVI functions connecting the mobile functions for the management, for the 5G management, yes, like the AMF, SMF, or UDM, and it is just also possible using the P4, but really we wanted to show here to the audience that we are able to implement the custom architecture for the VCSR. Why really the P4? Yes, why we need the P4 flexibility? Because that we are using P4 because we requiring the flexibility. Here on the left, you can see the reference design, reference architecture of the ORAN. You can imagine that every box here is the different service. Yes, here we are not talking about the separate devices, but of course the services could be implemented as the separate boxes, but really this is the applications connected together. And ODU, the DU or the distributed unit is if you can see, it is the third box from the bottom on the left side picture. And it has the many connections here that you can see that it has the 5 connections connected. And we today, for example, we need implementing this ORAN feature, we need to make this 5 connection to the different places, yes, in the data center. Somewhere in the network. And today this infrastructure is normally created as the MPLS, because we know that the thread boxes are inside of the antenna. Yes, it is in the mobile cabinet, so I have very close each other. But other boxes, other services could be very, very far from this model, depending on the what latency you want to achieve, that the different connectivity could be used here. Yes, and you see that right now this connectivity is very complex. You have many interfaces which represents different VRFs, the virtual routing function. With every of this connectivity has the different addressing, and this services could be located somewhere else as the part of the Kubernetes or Kubernetes based orchestrated by Kubernetes infrastructure. And thanks to the VCSR and thanks to the P4, we are able to handling of this connectivity, complexity of this connectivity. Yes, the system is going even much more crazy when we start talking about the new use case, when every telco operator are talking like the network slicing. In the network slicing model, you can imagine that for every new slice, yes, for example, like the ultra low latency, the eMMB or some mobile use cases for the industry, the machine to machine or the whatever else, the number of these connections is multiplied by the number of the slices. Yes, it creates the incredible. It creates the incredible complexity. Yes, and also with the network slicing, we have the requirements for the new protocols, because the MPLS, which is used today for the LTE networks, it do not fit very well. Yes, similar, the people are start talking about the SRMPLS or the SRv6. Yes, the currently such infrastructure doesn't exist. So thanks to the implementing this in the FPGA, and thanks to the implementing this using the P4, we have the both the flexibility and increasing the possibility. Yes, that let's talk a bit about how we implemented the VCSR. The VCSR normally is the component which has the few functions. Yes, a part of the router. Yes, it is of course the router, which could be the MPLS, segment routing MPLS, or the segment routing V6, which we are implementing as pure code. But also it has the other blocks which makes this design, P4 design, very specific to the VCSR. That I mean here, the clock synchronization, the QoS, or for example, the front haul gateway, which make conversion from the legacy LTE traffic, the SIP, called the CIPRI, to the eCIPRI, yes, which is used by the 5G new radio, or is used by ORAN. And this is, we in our model, we supporting model defined by the P4 application, by the P4 architecture. We have the P4 program, the router, and the route, this P4, we have the compiler for the FPGA, we have the SDK, which could be also used by the as the P4 runtime, or the some standard one. And we have also the data plane, yes, inside of the FPGA, which implements some table program by the P4 program of the data plane runtime. And we have this externs which we connecting to the data plane, with extern preparing the data for our preparing data for our data plane. And from our perspective, we have also the data plane runtime. This model here is the connected, in our case, with the commercial routing plane, to make sure that our tables, P4 tables, are programmed by the commercial routing plane. Let's make a short look to the how the P4 integration with the happens. Yes, with the commercial stack. We have the we supporting the few interfaces. Yes, inside our vRouter. Yes, from the perspective of the data plane, our P4 router has the interfaces connected, like we call the Smith-Hall interfaces. And it has some number of the interfaces connected to the host. And from the P4 perspective, we exposing all our interfaces to as the port representatives inside of the Linux kernel. And what our application is doing, using the P4, we're making the conversion from the MPLS to the IPv6, or we appending the MPLS to the IPv6, or we removing the MPLS depending on the destination. And we also handling the control plane, the inside of the P4 router, inside of the P4 code, we defining which packets are the control packets, and which packet are the data packets. And based of this, the P4 code, the tables set inside of the P4 code, some of the traffic is sent over the Columbia NIC or the Intel EA10, which we have on the card, to the software stack. And we are using the VLANs to determine the destination in the host. And the destination could be just the commercial control stack when we implementing inside of the software some distribution or the port dispatcher to the traffic received on the interfaces, which are next distributed to the commercial control stack over the Linux NetDevs. And additional applications is the, for example, the additional commercial application, the Intel FlexRun, which getting packets from the antenna, from the RU, which are the ECPRI packet, over, for example, the front hall gateway, which I mentioned that it is just some kind of the translator of the from CPRI to ECPRI. The traffic is forwarded to the Intel FlexRun, and Intel FlexRun just make conversion from the ECPRI to the IPv6, which is sent to the P4 router, and the P4 router is appending the MPLS or the set of the MPLS label or the SRv6 label or the SRv6 stack here, that depending what is the implementation. Yes, we here have with the P4 we have the very big flexibility from a customer's point of view, that we have the one hardware which can support the multiple use cases, and it is extremely important to the customers which are thinking about the long-term support. From the on to the control plane, only the control plane is all the control plane traffic is supported by the software here, that and it is provided to the commercial control stack. Yes, in the model here with the P4, we are able to provide with our hardware the model which is compatible with both of the P4 and compatible with the existing commercial application. Yes, I think which is the very big value from the perspective of the customer's view. But you can make a summary.
Yeah, thank you, Mirek. Yeah, to summarize here a bit, so we developed this virtual cell site router example from scratch within 6 months, completely validated. And the interesting part here is that the engineers on the team did not have any RTL skills at all. They were a set of software engineers. And actually most of the work spent was on aligning the P4 code with the commercial MPLS pipeline. The other thing we notice is that when you use well-defined host interfaces the P4 designs have, that can make them compatible with commercial applications like the Intel FlexRun or the commercial routing planes. And once you have an application like this ready, then it can be easily extended. For example, this example can be easily adapted to support segment routing over IPv6, or we can do new use cases based on the same architecture like network slicing. The challenges we've encountered during this development, the first one is on the architecture. So this might be a bit surprising, and it's a consequence of the flexibility actually of the FPGA. Normally an ASIC or an ASSP, like a programmable switch, has a P4 architecture which is fixed. It doesn't change, and you just fill in the P4 pipeline by your P4 program. But an FPGA is completely programmable. So also that P4 architecture needs to be designed, and that's not standardized. So you can have different architectures for different applications. So that adds an additional complexity on top of the normal P4 program. Of course, the externs that we have been using, and they still need to be programmed in some other language than before. In our example, they were all done in RTL. Furthermore, we need to continue working on simulations. The behavioral model is fairly limited, and finally the tool chain, the FPGA tool chain, needs to be integrated with more standard tools. In our case, that would be the Intel P4 software development environment. Thank you. That was all from us.
Okay, well, thanks a lot for the presentation. That's really interesting. Integrating FPGAs and P4 is really of keen interest for a lot of companies, including Keysight. And there's some other talks in the P4 workshop that the audience might want to look at, where the combination of switching ASICs and FPGAs is also employed. So it's a good theme to be running through the show this year. So I had some questions. One is, do you think it'd be possible to integrate custom P4 code on this platform with open source IP? For example, there's a project called Corundum on GitHub that's kind of an open source NIC that people are targeting towards FPGAs, including Stratix 10. Do you think there's a way to kind of merge those technologies for people to come up with their own designs?
Yes, it is definitely possible. Yes, because from the P4 perspective of our P4 pipeline, and even our P4 externs perspective, we are using. We need to have in our model. We need to have port which we connecting the host some way. Yes, and for our reason for compatibility with the commercial applications. Yes, like especially with the Intel FlexRun application, we are using the Columbia-ville NIC here as the port. But from the other customers, yes, who don't need to use the Columbia-ville, the special features of the Columbia-ville, and or they want to have the, for example, chip down design without the Columbia-ville, that they can implement or connect to the pipeline and any kind of the DMA. Yes. Which inside of Intel we also have some examples of the this DMA connectivity. Yeah? So that the different DMAs which could be used for the different reasons and can work easily with the P4 pipeline. Yes, because that we are using the standard interfaces, yes, between the DMA and our P4 pipeline, and you can treat our P4 pipeline as the some kind of the component which you must connect signals to your DMA. Yes, that we operating on the level of the packets. Yes, that you should provide. You can use any kind of the DMA, and you can provide the connect interface to make sure that the your DMA, custom DMA, whatever is the able to send and receive packet with the interfaces inside of the FPGA to be connect that way with our P4 pipeline, fully generated from the P4.
I think it's going to be a lot of fun for logic designers to hook these things up. It feels like a playground. I was a hardware designer back in the day, and this seems like a lot of fun. Here's another kind of a cross workshop theme. The table-driven interface, or TDI, is being promoted by Intel. It's an open source standard for a universal data plane programming interface, like to program P4 tables, etc. And there's another good talk about that in this year's workshop. Is there a plan to provide a TDI interface to the FPGA data plane? You didn't go into details on the block diagram, but I saw API there. Can you talk about that a little bit?
Yes. Yes, exactly. We are going into, because currently for this work, what we used here for this, the TDI is not used because we are using the P4 SDK, that let me say some internal one, and the TDI implementation for the FPGA is in progress right now, and in the current we're using some early access compiler and P4 toolchain, and when the fully validated the new version of the compiler will be available to the customers, that it will contain the TDI integration. It is just the part of the plans.
Yeah, like you mentioned, the TDI API is Intel is been pretty active in that development, and the ultimate goal is to have TDI supported on all our P4 targets. So while we didn't manage to use it in this case, any production version of it, this will definitely use TDI.
Is it fair to say that this could be just does this fit under like the IPDK overarching plan then, which is also a theme in this year's workshop?
Yeah, that's correct.
Great.
Yeah.
Perfect. Yeah, I can see all the pieces coming into play. One last question. I could ask 100 because I'm also a hardware guy, but we'll be kind to the audience and keep it shorter. Once this is production ready, do you think a non-FPGA, non-RTL expert will be able to get something up and running like with a hello world fairly easily?
Yes, in our model, really that model, what we're creating, what we're working with the final compiler is something what we call the push button model, yes. Even for the VCSR, that FPGA is designed that way that we as Intel preparing the P4 architecture, which or the P4 architecture components, yes, here, and we have the space inside of the FPGA to be filled by the design of the customer, yes. And here this VCSR example is just made that way, yes. We as Intel created the design, which is the most difficult part in the overall FPGA, the designing, yes, it is the creating of the connectivity to the pins, and we created the externs, which are written in the RTL, and next the development team, which has no RTL knowledge, no RTL skills, yes, they have also only the networking guys, the networking engineers, they created the working design, yes, so that normally it works, yes, that way, yes. And we believe that in the future that they will work with the other FPGA card vendors who can create, or the other customers who wants to create their own extents to be connected that way, in such model, yes, that it is. From our perspective, that really the tool set what we're creating is intended to such customers, yes. And currently we are experimenting with the different teams to check what is missing, yes. And it is like we have the early access toolchain because it is not fully released, and it is available for the qualified customers. And we're working with them in that way that the most of our customers or the users of our toolchain has completely know the RTL skills.
Got it. One more bonus question. You mentioned that BMV2 is a bit of a limitation for the simulation. I wonder if you could expand on that a little bit, and have you considered, for example, P4 DPDK as a more ideal platform for simulating, for performance and completeness?
It is possible. of course, but still, even in the P4D PDK, the biggest problem what we have with the custom architectures is the how to simulate behavior of our externs. Yes, for example, you can imagine that you want to implement or simulate the behavior of the QoS. Yes. Which, for example, the making the software model of the QoS, yes, of the hardware QoS, it could be very difficult, yes. And currently, it is the problem, but we see no issue to making sure or use the P4D PDK as the some prerequisite or some pre-step to as the first step, yes, to check how your P4 code is working before you will join the FPGA. Yes? So that FPGA or the other platform like Tofino, yes, or the other platforms supporting of the P4, yes, which has the more hardware base, yes. So that the P4 is the same. Additional problem with the using of the maybe the P4 the PDK for this reason is the that software implementation is the much more flexible even than FPGA. Yes, it is the FPGA is not ASIC, and we're saying that it is the flexible, but we can say the software is even more flexible. So with such total flexibility inside of the software, which is presented by the P4D PDK, that the implementing of the or the simulating even of the some behavior to get exactly the same behavior or on the functional level, like in software inside of the hardware, is possible only on some level. Yes.
Right. Understood. Well, great. Thanks a lot for this presentation. It was really interesting, and I think it's really relevant. And I hope people get the benefit of all your work in the near future. Thank you very much.
Thank you.
Thank you very much.